Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the Editorial Director with Data Science Central and also Chief Data Scientist for Data Magnum. I'd like to start off our event today by thanking Alteryx for sponsoring today's event. Alteryx is a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. I'd also like to take this opportunity to mention and show our appreciation for some of our other recent sponsors, including Qubole, Dell Statistica, Tableau, Microsoft, Exaptive, and Pivotal, to name just a few. Now, past webinars are available on demand at datasciencecentral.com, and if you haven't had an opportunity to view them, I encourage you to take a look. They provide some very useful insight into a wide variety of topics of interest to our data science community. Today's webinar is entitled Enhance Predictive Modeling with Better Data Preparation, sponsored by Alteryx. So before we begin, I'd like to briefly review the format of today's webinar. Today's webinar will be 1 hour long. We'll have two panelists that I'll introduce in just a minute. There'll be about 10 or 15 minutes of questions and answering following the presentation, and this event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. I'd also like to encourage our attendees to provide questions throughout the presentation. We'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speakers, Dr. Dan Putler and Matt Madden with Alteryx. Now, Dan is the Chief Scientist at Alteryx, where he's responsible for developing and implementing the product roadmap for predictive analytics. He has over 30 years of experience in developing predictive analytic models for companies and organizations that cover a large number of industry verticals, ranging from the performing arts to B2B financial services. He's co-author of the book Customer and Business Analytics, Applied Data Mining for Business Decision Making Using R, which is published by Chapman and Hall, CRC Press. Now, prior to joining Alteryx, Dan was a professor of marketing and marketing research at the University of British Columbia's Sauder School of Business, and also Purdue University's Krannert School of Management. Now, Matt is a director of product marketing at Alteryx. Matt has over 16 years of experience in the analytics and enterprise software industry, and during his career he's held roles in sales and marketing, both with the same goal, to help organizations realize the power and benefits that analytics can have on their business. So thanks for being with us today, Dan and Matt. We're looking forward to your presentation. Now, predictive modeling can be tough to implement in itself. Additionally, increasing data types and sources are making the data preparation process more complex. Now, experts know that while predictive modeling can deliver substantial business gains, it can also wreak havoc if the data used for analysis is not accurate or complete. So in today's webinar, we'll walk you through steps to build the right data set for more accurate predictive modeling, and you'll learn how to assess the quality of your data, cleanse and prepare data for analysis, decide what predictive modeling techniques to use. So Matt, with that, I'm going to turn it over to you. You can begin as soon as you're ready to go.
Thank you, Bill. And welcome, everyone. Thank you for taking the time to attend today's webinar, Enhance Predictive Modeling with Better Data Preparation. So today's webinar is really about educating you as users around how to build better predictive modeling. And really it starts with the data that you're dealing with. So the agenda for today's webinar is really, I'm going to give you a brief overview of who Alteryx is, for those of you who aren't familiar with us, and then go into some of the details around building that better predictive model. And really it starts with understanding what those business issues are. Then we're going to cover a couple different predictive modeling use cases, and then dive into really the crux of the presentation, starting with the right data. Now, data preparation and data hygiene really have different requirements based on what you're trying to do from an analytics perspective. Data required for BI and reporting is completely different than data that's required for predictive modeling, and Dr. Dan is going to go into that in more detail. And then finally, we're going to talk about, once you get that data in the right format, you understand what it needs to do, how it needs to be, then how do you choose the right modeling techniques to get started doing predictive modeling? So for those of you who don't know who Alteryx is, we are the leading platform for self-service data analytics. We empower analysts in the line of business to prep, blend, and analyze all of your data using a repeatable workflow, then deploy and share this analytics at scale to drive deeper insights in hours, not weeks. We have over 300 employees around the world, over 1,500 customers around the world, and our customers are so pleased with the way we do business that we have an average of 95% renewal rate from those customers on their licensing subscriptions. So what does Alteryx do and how do we work? As I stated, we're that leading platform for self-service data analytics. We give users the ability to access data from a wide variety of sources. It can be from the desktop. It can be in a cloud-based environment. It can be from a CRM system, ERP system, relational database. It doesn't matter. We give you that ability to access that data from a wide variety of sources. Once you get access to that, you can prepare and blend that data in a repeatable workflow environment, a drag-and-drop workflow that requires no coding, no SQL coding, no analytic coding or programming. We even give you the ability to enhance and enrich that data with packaged third-party data that we offer from Experian, Dun & Bradstreet, TomTom, and the Census. Once that data is prepared and blended, we then deliver over 60+ tools for advanced analytics, giving you the ability to do anything from spatial to statistical, predictive, and even prescriptive analysis in many cases. And then you can share these analytic results in a wide variety of formats. You can do it in the form of an analytic application, out to a visualization tool such as Tableau, Click, Power BI, or even Salesforce Wave, or you can output it directly back to a database, back to your desktop in the form of an Excel file, and much more. So with that, I'm going to turn it over to Dr. Dan to really go into the crux of the presentation itself.
Thanks, Matt. I'm going to start by talking a little bit about understanding the business use case, and in particular, my philosophy about how you think about the purpose of predictive analytics. And ultimately, the first thing we need to do when we look at the business issue is we need to determine exactly what decision needs to be made. Now, in some sense, what we're trying to do with predictive analytics is provide the information that's going to appropriately inform the decision that needs to be made. So in order to come up with the right data, we need to come up, or with the right analysis, we need to determine exactly what that decision is in order to provide exactly the correct information for it. Now, that's true with a lot of business analytics and business intelligence reporting. The thing that's a little bit different about predictive analytics compared to other sort of business intelligence activities is that in business intelligence activities, typically the information is going to be provided by querying existing historical data to begin to inform that decision. In the case of predictive analytics, that historical data can't be directly queried, so what we need to do instead is predict values or predict the associated information, and that's what's going to inform the underlying decision. The next thing that kind of comes into that is that we need to determine exactly among the existing information that we have available to us, that information that we can query, is what information we need to take from it in order to come up with predictions that is going to provide appropriate information for the particular business issue that needs to be addressed. And to do that, it's frequently really helpful to develop some sort of mental model of the underlying process that helps to suggest the set of variables that we're going to want to look at that we can gain access to historically that can then allow us to predict likely outcomes in the future. So the mental model process is really kind of critical in determining what variables you need. A lot of the data is likely to exist in your own databases, but some additional data is likely to be needed in order to address particular questions. And in order to do that, to determine what data that extra data is, frequently coming up with a mental model is going to be really useful for doing that. What type of analysis the next thing that needs to be determined is exactly what kind of analysis is going to be able to provide the exact information needed to inform that particular decision. And when we talk about that, and we'll get into it a little bit later, we'll talk about different modeling methods, and this is exactly where the modeling methods come into play. So to make things a little bit more concrete, I want to give a couple of underlying business use case examples, and I'm going to kind of build on those to see how everything sort of fits together. The first of those is how much electricity does a utility need to have the capacity to supply for any given hour tomorrow. The second one is a very different use case, and that is to which of its customers should an outdoor sports retailer send a paddling sports catalog. I'm going to get into the first of those examples in a little bit more detail. And really when we look at that question of how much electricity does a utility need to have the capacity to supply for any given hour tomorrow, underneath it are really two very specific business decisions that have to be made. The first of these is which of our existing power plants should we start to bring online or start to take offline. Now, bringing power capacity up at any given moment in time is going to take a number of things in order to do that, and it's going to take time to bring plants up or take them down. The other option that we have is that we could potentially either buy or sell electricity in the spot market, and there is a spot market for electricity. So we need to make a decision about that. Now, the trick associated with it is that we have to make those decisions a day before. And the information that we need to have in order to make those decisions is how much electricity will be demanded in each hour of the day tomorrow. Now, at the time that decisions are being made, we don't know that information. But instead, what we can do is begin to come up with predictions of how much electricity we expected to be demanded. And based off that expectation of demand, we can make appropriate decisions about what we want to do with our generating capacity, either through taking down power plants, bringing them up, or buying or selling power on the spot market. Right? The next thing that goes into this is thinking about what factors are likely to drive the demand for electricity in any given hour tomorrow. This is exactly where having a mental model of the process can be very handy. Now, what I'm going to do is just take, about 10 seconds, 15 seconds for you to think about this for just a moment. Try to come up with a mental model of how what's going to drive electricity demand, and we'll begin to talk about the variables from information that we can know historically that we can take advantage of. So just take a moment and think about it. Okay, so in the purposes of brevity, I'm now going to look at what we looked at when we thought about how do we model demand for electricity in each hour of the following day. And there were a number of factors that we came up with. The day of the week, because what we would expect is that demand during weekdays was likely to be higher than on weekends. Also the hour of the day, so when people get started in the morning and come home in the evening, there's likely to be a spike up in electricity demand as people start to turn on their air conditioners, they start to run their dishwashers and their washing machines, a number of things along those lines. And the temperature that hour and the preceding hour. Now, one of the most critical uses of electricity is for space cooling and to a lesser extent space heating. And what we'd expect is the temperature would matter. But one of the things that goes into this is that there's sort of inertia in people's behavior. So it seemed quite plausible to us that people would have it get warm or cool for a while, and then at some point kind of realize that they need to do something with their thermostat, and at that point they would respond. So there would be, in some sense, a lag between the temperature and people's electricity demand. The other thing that goes into it is the month of the year. In some sense, you would expect electricity demand patterns to be very comparable between December and January, but the difference between December and January are Christmas lights and other Christmas decorations that wind up using electricity to power them. Now, one of the issues that is really important that I already mentioned is that the temperature in each hour tomorrow as well as the hour before tomorrow is going to matter a great deal. Now, in this particular instance, we can't query historical data to look at that particular issue. So what we need to do instead is provide predictions of the temperature for each hour tomorrow and use that as input into our predictions of what we're expecting electricity demand to be. So what this leads to ultimately is that we're going to have to sit down and create two predictive models in order to begin to address this particular question. Now, when we look at hourly temperature, there are a number of things that we can take advantage of. Forecasts of high and low for the day from the National Weather Service or some other appropriate organizations, such as in the U.S. is AccuData, the Weather Channel, a number of other providers of weather data. We need to know the numbers of minutes since sunrise or sunset at the start of each hour. The basic idea is that if it's been sunlight for a while, you're likely to have greater temperatures than you would, it's going to have an influence on the temperature. And the temperature of the same hour on the previous day. Now, sort of interesting, if we look at these two factors, it turns out there are really sort of two literatures that look at forecasting hourly temperatures. And one of them relies really heavily on the number of minutes since sunrise or sunset. The other of them relies very heavily on temperatures for the same hour in the previous day. We decided to look at both of those factors in this particular model. Those factors are likely not to be in the company's database, and so as a result, we wound up collecting that data separately. And again, the mental model is really useful for determining what data outside the organization is likely to be useful for making predictions that are going to inform decisions. Ultimately, we created two predictive models, as I've already suggested, one to predict hourly temperatures the next day, and then a second one to predict hourly electricity use given temperatures and the other factors that I've just mentioned. Let's move to the second example, which is a paddle sports example. And in this particular case, the criteria or the specific information we want to know is really specific. To which of its customers should an outdoor sports retailer send a sports catalog? The answer to that question is definitive. Send it to any customer where the full cost of sending a catalog is less than the expected margin dollars, which is the item less the item cost, item price less the item cost, from the items a customer would purchase from the catalog, right? That's a great criteria, and it answers the questions precisely, but the real trick is we don't really know a priority which specific customer should be sent a catalog, since we know what the criteria is of whether or not we're going to send it to them, but knowing whether or not a particular customer meets the criteria is a completely different matter. And in order to begin to address that particular question, what we're going to need to do is develop a predictive model based off of available information that will allow us to estimate or predict the likelihood or the probability that that particular customer is going to be worth sending the paddling sports catalog to. Right? In this particular case, the way we would do this is typically come up with two different models. The first model would predict whether a customer will purchase anything from the catalog at all, and then a second model will estimate or predict a model of the margin dollars a customer will generate conditional on using the catalog. So in some sense, what we have is down below, the first one is the probability of whether or not they'll respond at all. The second one is the conditional demand or the conditional margin dollars we expect from that particular customer. To come up with the actual answer, we need to take a product of those two quantities, the probability that will respond times the expected margin dollars if they do respond. So that will give us the unconditional expectation about how much we expect that customer to spend, or how many margin dollars we can expect to get, we will receive from that customer if we mail them the catalog. Okay. In terms of selecting variables for the two models we just gave, we can identify a number of different variables that could be used. One critical thing is that we need to be able to know this information prior to sending a customer a catalog, right? Information that is known only after we send the catalog is going to result in leading us astray. So what we can run into is causality problems. And I've seen a number of cases where these sorts of causality problems have crept up. So an important criteria is that in developing predictive models, you have to know you have to use information that would be available prior to the decision a customer would make. Right, and there are a number of factors we can begin to look at that fit into that category. Naturally, what comes to mind are demographic and socioeconomic information, things like age, income, and family status. We can also imagine that the location of the store with respect to what state that store is located in, along with information about its proximity to bodies of water, such as sea, lakes, or rivers. And something that it really comes up frequently in customer applications is looking at past purchase behavior. And that's typically measured using the concept of recency, frequency, and monetary value, which is frequently labeled as RFM. Recency is the most recent purchase of a particular type a customer has made from us. Was it, did they buy a paddling item 1 month ago, 5 years ago, et cetera? The frequency with which they buy items. Do they, within a given period of time, say 1 year, have they bought items 1 time or they bought items 10 times? And the monetary value of the items that were purchased within that particular observation period that we're looking at. Generally, for RFM measures, it's best to look at things within an observation period. Otherwise, you wind up essentially implicitly shrinking down what your customer list looks like. So those measures have to be used carefully, but when they are used, they're frequently very powerful predictors of the underlying phenomena. All right. We also need to have observations on an appropriate target variable. Right, so we need to have some similar event that we can take a look at, and in some cases we can do this readily from historical data. So if we do a paddling sport catalog every year, then what we can do is look at what happened last year associated with that paddling sport catalog. If this is the first time that we've offered it, we don't have historical data that we can rely on. So what needs to be used instead is some sort of a test approach. Where we send the catalog to a sample of our customers and then use this data to predict the behavior of all our customers. So we start with a small group, say 5% of our customer base, create models based off that, say, randomly selected 5%, and then use those models to predict the behavior of the remaining 95% of our customer base in order to come up with good estimates of the expected margin dollars from sending each of those customers a catalog. Right. Now at this point it makes sense to get into sort of the nitty-gritty of developing a predictive model. And it turns out when we look at predictive models, there are a huge number of different modeling techniques that have been developed over time. Some of them are tried and true, like linear regression and logistic regression. Some of them are comparatively newer, such as random forest models, gradient boosted models, and a number of other things that have been developed within the past 20 years or so. And one of the things that we need to begin to think about is what are the appropriate modeling methods to use. And in this particular regard, I have really sort of two recommendations. Selecting an appropriate modeling method is driven by the underlying nature of the target variable we want to predict. So the critical difference between target variables, are they categorical in nature? So do they represent, say, a yes-no decision or selection of option A, B, or C? Or are they numeric in nature? So sales are frequently a numeric data element. And it turns out the modeling methods you use for categorical variables and numeric variables are different from one another. So that really is the underlying thing that begins to drive the selection of a set of proper techniques to look at a particular question. The next is selecting a specific model, and hence the underlying model method itself. And in this particular case, really what we ultimately want to do with predictive models is be able to predict what people are going to do in the future, given information that we know about them now. And really the criteria we need to use when selecting between different models is this notion of which model has the greatest predictive efficacy. And predictive efficacy can be determined practically a number of different ways. If there's a lot of data available, and really kind of the traditional way to do it is using basically a sample where we estimate a model, so an estimation data sample, and then we have a second sample, which is a validation sample, or frequently called a test sample, where we look at the predictive efficacy of models created in the estimation sample in its ability to predict new data, the data that is in the test or the validation sample. And it goes by a number of different names. And the other ways that we can do it is by using methods that are known as resampling methods. The most common of those are cross-validation, and another of those is bootstrap, where we take some of our data, we estimate a model, and then predict new data based off of it. And frequently what we'll do is we'll rotate through all of our data, in some cases using it as what we're using as a sort of mini test sample, and in many instances using the bulk of the data as a training sample. Right. In terms of, and I just mentioned above, selecting the appropriate methods really depends on the nature of the target variable, and there are really two basic approaches that you can look at. One are known as classification models that predict a category into predict a particular case into a set of different categories. So in this particular, in a number of particular cases, we may be looking at what determines whether or not a customer is likely to say yes or no to a particular offer, or alternatively, which of several options they might select. If the underlying value that we want to predict is a continuous variable, some sort of a quantity, then typically we're going to use some sort of a regression model. All right. If we go back to the use cases that we talked about earlier, so the electricity demand and the paddling sports category catalog example, what you're going to find is whether a customer will respond to the paddling sports catalog is a classification problem, while the margin dollars from a customer who receives the catalog or the hourly temperature and electricity demand, in the electricity demand example, that's going to involve regression analysis, since both electricity demand as well as temperature are continuous variables or numeric variables, and the same is true with margin dollars. All right. Now let's kind of go into some elements of the nitty-gritty of data hygiene in this particular case. It turns out if you come from a business intelligence, traditional business analytics background, it turns out that the level of data hygiene that's needed for a predictive model is considerably higher than it is for sort of traditional BI reporting and for dashboarding, right? If you look at cases, and probably a good example to look at is if we're some sort of a retailer, we can look at country of origin of our customers. And we may be US based, and so actually, you know, by far and away, the bulk of our customers reside in the US, but, you know, there'll be a few elsewhere. And when you look at reporting, you may, you know, you wind up doing pretty well if you can deal with those sorts of variables in a very reasonable sort of way. You just have categories with a very small number of respondents within them. If you have missing values with some of your data, you just create a new category which indicates that this is a not available or a null category. So you can just kind of quickly create separate categories for those individuals that have either missing data or there are small numbers of records in different categories. Right. It turns out there are a number, and that works really well for business intelligence. It works much less well when we look at predictive analytics. There are a number of common data hygiene gotchas that are associated with predictive analytics. The first is fields with missing values. Some modeling methods, and it turns out different modeling methods handle missing values in different ways. In some cases, very few methods can actually handle missing target variables. Actually none of them, and it turns out other methods handle missing predictor variables in different ways. In many instances, a lot of the traditional methods like, say, logistic regression or linear regression can't really address missing values in any of the predictors, and so the typical things that they wind up doing is dropping those records from the data. The other thing, though, with tree models, they can take advantage of something known as surrogate splits, and so they can actually cope with missing values. Now, one of the things that you run into is that when you have situations where you are using different modeling methods and comparing the efficacy of those models, in some sense, the underlying models themselves are based on different data. In the case of a model that is using a decision tree-based method, it can take advantage of all the data, whereas if you have missing values in your predictors, the more traditional methods are going to have records that have been dropped out. So they're not really working with exactly the same set of data. And so that becomes an issue associated with model comparison. The other thing is that you frequently find situations where categorical variables have very little variability. And we also run into kind of related problems associated with there may be a small number of counts for, the non-dominant category. So if we sort of looked at the example that I just gave, which is we're a U.S. retailer and we're looking at country of origin, what we may find is that 99% of all of our customers reside in the U.S. with only 1% residing outside the U.S. And in those particular cases, you run into issues associated with how do you deal with those other countries. And besides, is this variable going to be particularly useful to begin with at all, given that 99% of people reside in the U.S.? What do you do with that particular one customer that happens to reside in Bahrain? And so it becomes a bit of a problem, and it leads to underlying problems associated with what we do for prediction. So we sit down and create a model. We may have missing categories from what we had in our estimation or our training data set when we look to predict new data. So we may have had no customers from Bahrain in the data that we use to create the model, but suddenly when we use the model for scoring purposes, we suddenly have to deal with a customer that was residing in Bahrain, and the models really can't come up with, in many instances, come up with reasonable predictions for those particular individuals. Right. The final thing that we run into is frequently what we run into is that we have categorical variables that are hidden as integers. And this turns out to be sort of problematic from a modeling point of view. And probably a good example of that one is we may have a situation where we're looking at a customer who's selecting between 3 different options, option A, option 1, 2, and 3. And we may have labeled them as 1, 2, and 3, and we may have left them as integers. In that particular case, when we go to create a predictive model, the nature of the predictive model we create is going to differ greatly depending on whether or not we identify, the options 1, 2, and 3 as categories, or if we identify them solely as integers. If they're identified as integers, what we're going to then do is treat them as if they were quantities and suddenly run a regression algorithm against them, as opposed to running the correct classification methods in that particular instance. If they are one of the predictors, it also differs on how they are handled in the model building process. So what we want to do is make sure that things that are really categories in nature aren't simply disguised as a set of integers, because it's going to run into a number of different problems. All right. At this particular moment, I've got some ideas what we want to do to deal with the issues that I just identified. So what do we do in terms of addressing fields with missing values? Well, for predictive variables, it makes sense to begin to impute those missing values. And I've got some recommendations about how you really want to do that. And it turns out there are a number of different ways you can do it. In the case of numeric variables, using a fixed value, such as the mean, median, or 0, is commonly used to address these missing values. In addition, we can provide a categorical variable that is created that indicates whether or not a particular value of that predictor has been imputed or not. So it says, by the way, this one was actually missing, but it's sitting down with a value of 0 at this moment in time. My recommendation is to use zero values along with a categorical variable to indicate if a value of a variable has been imputed or not. Right? In terms of categorical variables, they can be replaced with a new category indicating that the value was missing. So we can take the nulls or NAs and basically create a category that says missing. This missing category will at least begin to adjust for the fact that it's missing. And the other way that we can begin to look at it is using the mode value of the variable. Now, one important thing in this particular instance is that sometimes missing information, particularly that's categorical in nature, can convey information in and of itself. A classic example of this is someone who is looking to apply for a credit card, and they non-reported their income category. In that particular instance, the fact that they've elected not to report their income category provides information in and of themselves. As a matter of fact, the examples I've seen, they're more likely to be a bad credit risk as opposed to people who actually did report their credit, since in some sense what they're trying to do is hide something in that particular instance. Right? There are also model-based methods that help us to replace missing values through predicted values of the missing variables. Now, which one of those you select is going to be critical. If you think that there may be some sort of strategic behavior, like going back to the credit card example of not reporting income, you probably don't want to impute the values, or you don't want to use a model to impute the values. Instead, really what you want to do is take advantage of the fact that you can indicate that that category is missing and get the additional information that may be available from the fact that it has been non-reported. Right? In terms of, and the final things, records with missing values for the target variable should be filtered out of the data. In this particular case, generally the only thing you're going to do is run into potential problems associated with the modeling methods, and ultimately really what you're trying to do is predict the target variable. So, you know, using imputed values of the target variable is going to reduce your ability to predict that target variable going forward. All right. The next issue that we really want to talk about is data hygiene for addressing problematic categorical variables. And in particular, addressing categorical variables which are dominated by a single category, therefore having little variability, depends on the amount of data that's available to us for creating a model. If there's lots of data and there's a reasonable number of records, and as a rule of thumb, I kind of tend to use 20, in each of the non-dominant categories, then including a field in the model is a viable choice. Otherwise, it makes sense to include these fields otherwise it makes sense to not include these fields as predictors. So going back to our country of origin example for a retailer, and we've got 99% of our customers in the U.S., if we have a fair number, if we have a lot of customers, you know, say if we're looking at hundreds of thousands of customers or millions of customers, then that 1% represents a fairly large number of potential respondents. In those particular cases, we may want to hold on to that data. Now, there is sort of a side note to it, which is the next one, and that is in the case of categorical variables with categories with few records, it makes sense to combine categories together. The combination of categories should have a sound logical basis as opposed to being combined due to having a similar relationship with the target field. Now, what goes on when we have small number of respondents in a particular category, we run into problems with random sampling variability. And in some sense, one way that you could begin to imagine to combine those together is to take categories where you apparently have a high response, potentially due to random sampling error, and combine them with other categories that potentially have a high level of random sampling error. And as a result, they become stronger predictors from a power point of view, but the underlying reasoning for doing that really is faulty because you may really be introducing, you know, you're basically looking at noise and you're aggregating the noise together to make the noise effect even stronger, which is going to be problematic. On the other hand, if you have a fairly large number of records, right, so if we look at what's going on with, you know, the 99% U.S. customer basis, if we have several thousand non-U.S. customers, one thing we can look at is for some countries we may have, you know, a fair number of individuals that come from that country, say we have 150 from Canada, but for other countries we have a smaller number. So from England, from the UK, France, and Germany, we may have a very small number of customers, but if we sit down and think about aggregating those customers together, since they're going to be doing overseas shipping, et cetera, we have a logical basis for combining those customers together in a reasonable sort of way, and therefore we can aggregate that category down or aggregate some of those categories down to reduce the number of categories, but still have a sufficient number of observations in each of those categories, right? And then finally, fields that use integer values, you know, to represent categories, the easiest way to deal with them is to change the underlying nature of those variables. So if we have integer values of 1, 2, and 3, we can just change the data type to be a categorical or some sort of a string type, and they're going to likely be interpreted properly as being a categorical variable. So to quickly sum up, what you really need to do is clearly define the business problem or the business issue, right? You need to provide exactly the information that you're going to need predicted values for in order to address the underlying management issue that you're facing. And this is going to typically be improved if you create some sort of a mental model to do it. Right? You want to start with the right data. And again, that mental model helps you point you to the right data in terms of what is likely to be predictive in that particular case from the existing historical data that you can take advantage of. Again, you don't want to take advantage of data that you're only going to know after you've taken some action because you can run into issues associated with causality. So you want to have the appropriate variables to begin with, and you also want to be in a situation where you will always know the answers or know the values of those variables prior to taking some action. All right. As I've indicated, data hygiene requirements for predictive modeling are more stringent than for business intelligence and reporting. And data variable type, numeric or categorical, matter, and they matter both for selecting an appropriate modeling method. Should we be using a classification method or a regression method? And when imputing missing values, and just as I've indicated before. And then finally, the volume of data can be critical when addressing problematic categorical variables. Do you have sufficient number of records for those thinly populated categories in order to make valid inferences based off the underlying behavior from members of those particular categories? And with that, I think we're moving into question and answer period.
Well, Dan, Matt, thanks for that excellent presentation. And Dan, obviously you've covered a lot of ground in very little time. And obviously there's a lot more depth behind this because we have lots and lots of detailed questions. But we'll get started on today's Q&A session. And I want to thank the audience for their participation. There are a lot of questions that have come in during the presentation, and we'll do our best to get through them all in the time remaining. So during this Q&A session, I'll leave up this screen with contact information for Dan and Matt if you'd like to contact them following today's webinar. So let's get started, and let's start with something general. Do you have any recommendations on how to get up to speed with predictive analytics as an entire field?
Yeah, I having seen what's gone on with this. So again, prior, as was indicated at the top of the session, I spent 20 years before joining Alteryx as a professor of marketing and marketing research. At the time, we sort of created one of the first courses in business data mining that existed in a North American business school at the University of British Columbia. What we kind of did is we looked at what was going on, and this was back in 1999, so it was a while ago, is that companies in the Vancouver area that were suddenly engaging in predictive analytics in the early days, largely what they did is they were, looking at small projects to get started. So they kind of got, they got an understanding of what was going on. They wound up using any particular tools that they could get their hands on. Frequently what they did is we began to read a set of books that were out there that understood what was the nature of the predictive analytics process for business decision making. And they really kind of got started that way, starting small, building up, gaining proficiency and skills associated with what they were doing. In terms of books to look at, there are a number of them on the market at this moment in time. The top of the hour again, there was an indication of the book that I had written with Bob Kreider at Simon Fraser University that really goes through a number of case examples and begins to bring it up and give people an understanding of what the underlying methods are, what are the kinds of problems that they can be used to address. And so a combination of learning by doing and reading is a really good way to get started.
Thank you. Thank you for that excellent answer. Now, a lot of the questions that have come in reflect the emphasis in your presentation on data prep and preparation prior to modeling, which is very appropriate. But we also have some questions about specific modeling techniques, and I'd like to start there. For example, can you tell us what types of predicting modeling techniques Alteryx supports, and particularly, since we didn't cover it during the presentation, can you speak to the issue of neural nets? Sure.
We cover pretty much the broad range of modeling techniques that are very common in predictive analytics practitioners' toolboxes. So for classification, we include logistic regression models. Neural network models can be applied to classification problems. Decision tree models, in particular, we use recursive partitioning currently within the tool. random forest models, which is an ensemble of decision trees, gradient boosted models, which is another ensemble of decision trees, naive Bayes classifiers, which is again another classification method, support vector machines, and I think in total there's like 8 models that we have available for classification. For regression models, we have traditional linear regression, as well as a number of the methods I've already indicated use different criteria for classification versus a regression problem, but they have analog methods that work across both of them. So decision trees still work in that particular case, and decision tree-based methods such as gradient boosted models and random forest models work. What differs when you go from a classification problem to a regression problem is the underlying criteria that it is using to create those models. So, and that quickly gets into technical detail, but the methods are clever enough to recognize whether or not you're dealing with a classification problem or a regression problem, and will behave accordingly. That actually feeds back to my response about it's really important to deal with predictor or deal with variables that are really categories that are masquerading as integers. Because the methods, if they see it as an integer, will assume it's a quantity and deal with it as a regression problem. If they see it as a set of categories, they'll deal with it as a classification problem.
Right. And let me stick with neural nets for just a minute, because neural nets are frequently a very powerful way to get a somewhat more accurate model, depending on the data. But they have the requirement that the data be normalized, that is, reduced to a scale between 1 and -1. Is Alteryx going to alert me if I try to use a neural net that I have to do that, or will it automatically do that? How much will Alteryx keep me out of trouble?
So what we have is a question, and it turns out it can be between 1 and -1. It depends on the nature of the underlying problem that you're dealing with in terms of the scaling. But we do include within our tools, so we didn't show it today, but it's a drag and drop interface. And so what goes on is you drag the appropriate tool onto the canvas. It has a number of configuration options, and typically we kind of set it up with a set of base configuration options and then move into other ones. And one of those options within the neural network tool is to do an appropriate scaling of the underlying target variable. It's
right.
a checkbox option.
Okay, good deal. Moving on to the number of audience questions about data prep and dealing with missing values and those sorts of questions. Let's start at a really high level here with a really good question, I thought, and that is, at what percentage of missing value do you begin to think about just abandoning a feature altogether? Is 20% missing value enough to make you want to throw it away, or is 20% enough to make you want to keep it?
And that's a good question. And I think in some sense, it's going to depend. I mean, this is in those cases when you get to the higher percentage of them, this is where it's really important to include an indicator of whether or not it was missing or not. And I think it's also going to differ as to whether or not, to a certain extent, in my opinion, whether or not it's a categorical or a numeric variable. If it's a categorical, I think I'm willing to tolerate a higher percentage of missing values than if it's not. Now, I think only having 20% live values is a problem, and so I would probably set, and this is just sort of rule of thumb, based on experience, I get really nervous when things are under, 50% actually there. Because what you're trying to do with that categorical variable is in some sense statistically control for the fact that you've got missing information there. And at some point when it just starts to dominate what you're doing, there's ultimately really no there. So I think 20% is too low. When there are only 20% non-missing values, I would tend to steer clear unless there was really some specific reason as to why I wanted to include it. Now, in some cases, right, in some cases, so if I'm looking at missing values, and let's go to a financial services example for consumer banking, and I'm looking at, how much funds do they have in some sort of a check, in some particular type of savings account, frequently those missing values actually are not truly missing. It means that they have no transactions associated with that particular time of account because they don't have an account of that type. And so in that particular case, imputing 0 and then adding an indicator variable is probably going to be a reasonable thing to do. In other cases where there really should, in that case, missing values are in some sense acceptable because they indicate that they don't really have an account. If it's just like truly missing, there's just no information available, and in that particular case, there is information available. It's just telling you they don't have that type of account. But if there's no information available, then I would tend to ratchet that down. So I'm hedging a bit, but it depends on the specific situation as much as anything else.
Right, and just as frequently we'll run it both ways and see which works better.
Yes, predictive efficacy is ultimately the name of the game.
That's right. That's right. So, to come kind of all the way back up to the top of the scoreboard, when you're first presented with a set of data, I guess when you are exploring it, the first thing that we all want to do is to look for outliers and try to decide if the data is actually homogeneous. And for example, if the data is not homogeneous, we might want to segment it and actually turn it into 2 or 3 or 4 different models for each subsegment. Can you talk about how Alteryx can support us in making those decisions?
Yeah, and there are a number of ways to potentially do that. There are sort of model-based approaches, and in some sense, that's particularly in the marketing research literature that is dealing with latent heterogeneity within the data, and so there are a number of mixture model approaches that have been created to deal with that. Alteryx doesn't implement those approaches, but Alteryx does have the ability to do analyses where you can look at things based off of different groups within your data. If you have some sort of an indicator variable within it, and it's say a continuous variable, you can sit down and look at those different groups. We have a set of clustering algorithms. So if you want to start out with and cluster your data to begin with, and then develop a model for each of those clusters that is supported within the Alteryx environment. So there are a number of ways that you can begin to look at that issue within Alteryx.
Good, great, thanks. And by the way, in terms of modeling, does Alteryx support or integrate with some of the common languages and packages like R or PMML, or does it support SAS or SPSS or other common modeling platform tools?
Sure. So if you look at what we're doing from a modeling point of view within the predictive analytics capabilities in particular within Alteryx, that is really based on R. So we basically support, all of our predictive analytics tools really are using R under the hood. The way we've set things up is that a user of those tools can look at exactly the R code that we're executing. In some sense, at this moment in time, best way to view from a predictive analytics point of view, what Alteryx is doing is really a script generator for R. A number of our other tools, all of our data blending tools, are inherently purely Alteryx. The same is true with most of our spatial analytics tools. But in terms of predictive analytics, right, we've done that entirely based on the underlying R language. We have some capability to take advantage of Python, and that's likely to increase over time. So both of those are going, languages that we can, we can work with them now, but it kind of involves running a script from a command line for using Python, but we will begin to integrate Python into our capabilities going forward. If we look at SAS and SPSS, those are closed proprietary systems. We have the ability to read SAS7BDAT files and SPSS SAB files, and also to write those formats. But you can't use really SAS nicely directly, same as SPSS with Alteryx, largely because of the closed nature of those systems.
Okay, all right. Now, one of the first things that we all face when we're facing a new predictive modeling problem is deciding which features are important and which features aren't. and you talked a little bit about that, but would you suggest some of the tools? For example, is there principal component analysis, or what are the tools that are available in Alteryx to help us pick which features to use?
Sure. We provide the ability, we provide a principal components tool. Again, it is an R-based tool, and we can take advantage, of R's principal components capabilities, so that can be set down and take advantage of. So you can run a dimensionality reduction on the variables and use the principal components directly, or look at which principal components are most highly loaded on, which variables most highly load on the principal components, and select variables based off of those loadings. So both of those are possible within Alteryx. One thing I might kind of suggest for those of you who are kind of interested in Alteryx and really haven't seen Alteryx at this moment in time, if you go to the Alteryx website, www.alteryx.com, we have a trial version of Alteryx which you can take advantage of and download and get an up close and personal sense of exactly what predictive methods we cover within Alteryx.
Okay, yeah, terrific, and obviously a little exploration would be appropriate. And I must say the audience has given us a lot of questions, and it clearly indicates that these are folks that are either doing predictive modeling or are getting started with predictive modeling. And appreciating that our time today was so limited, I think you did a great job in covering the broad areas, but let's dive down. We've got time for a couple of more questions. Actually, let me take a bit of a digression here. There is a question about deep learning, and I know that deep learning is probably outside of the scope of Alteryx, but maybe I'm wrong. Tell me where Alteryx is headed with respect to deep learning.
And that is, something that we're currently looking at. I mean, the important thing to understand is that deep learning is, to be honest, the next generation of neural network models. And so as a result, we currently support neural network models. We're limited in the architectures that we're looking at. When we look at deep learning, what we're likely to do is there are two ways that we kind of interact with things. We interact with things on a particular analyst's desktop using the desktop designer, and we use R locally for that. We also have the ability to do things in database. And so likely what we're going to find that future deep learning capabilities are going to be done directly on the data itself. And so we're going to be done within the database. I will say that if we look at it, one of the things that, from my experience, that I get a sense of is that deep learning and neural networks become really critical when you're looking at sort of natural phenomena. So if we go back to the use case that we did on electricity demand, we found that predicting hourly temperatures based off of physical quantities, the best model in that particular case was a fairly elaborate neural network model to look at that particular issue. When we looked at electricity demand, what we found is a random forest wound up working best. And that's kind of consistent with a number of things that I've seen. So if you look at deep learning sorts of applications, they tend to be oriented towards sort of natural phenomena, pattern recognition, for instance, things related to that. I find when you get humans involved in terms of decision making, frequently the tree-based models wind up being the preferred model. So you don't want to kind of look at just at deep learning or neural network-based approaches in the absence of these other methods. I think it depends on the underlying situation that you're looking at.
Well, Dan, Matt, thanks for some great answers to some very good questions. I must say this has been a fun presentation. For all of those of you that asked questions that weren't answered today, we'll be sending all those unanswered questions to Dan and Matt and the Alteryx team so they can follow up with you after today's webinar. Now, I have just a few quick announcements. If you would please mark your calendars for July 12th. That's our next DSC webinar, which is exploring 7 kinds of data stories, sponsored by Tableau. Also, today's taping will be available for on-demand viewing later today and can be found on the home page of Data Science Central in the Webinar tab located at the top of the page. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions, and a special thanks to Alteryx for their sponsorship, and our speakers today, Dr. Dan Putler and Matt Madden for their insights into today's topics. Now, my name is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on July 12th. Have a great day.